Hey everybody, this is Dr. Walker. In this video, we are going to go over the example from video 218, and it was from the video on the electron volt. So let's go ahead and take a look at this problem. An electron is accelerated from rest through a potential difference of 100,000 volts. Find the speed of the electron. And this picture here just shows a particle accelerator, and it's used in a lot of experiments, and it speeds up the electrons and mashes them into other things. Definitely look into it if you are interested. So, we're looking for the speed of the electron. We know that when an electron is moving through a potential difference, that it's going to, the kinetic energy and the potential energy is going to change. So I want you to take a moment and think about your approach to this problem. What equations are going to be relevant, and what are the givens in this problem? Okay, so let's start by writing down the givens. We have, the only thing that seems to be really explicit is that there's a potential difference of 100,000 volts, so that's delta V, 100,000 volts. Now, whenever we have this type of problem, you know that I like to draw my plates. And since it's an electron that's moving, then I like to draw a negative on the left and a positive on the right. The electric field goes to the left, but the electron is going to the right. Again, this is just visualization purposes. There's a potential difference here, delta V of 100,000 volts. And we want to know, well, what's going to be the final speed of the electron? We know that it's going to speed up because it's going to the right towards where it wants to go. It's experiencing that force to the right. So, with that in mind, if we know that it's going to speed up, its kinetic energy is going to increase, then we know that we want to find the kinetic energy first, and then we can relate it to the speed. The equation that we have for the change in kinetic energy, and I know I said we were going to write the givens first, but sometimes you kind of do both at the same time to figure it out. The change in kinetic energy is negative Q delta V. That being said, we also learned in this video that when an electron is accelerated through 1 volt, it gains 1 eV. Well, how many EVs do you think it gains if it's accelerated through 100,000 volts rather than 1 volt? How many EVs, electron volts, do you think that corresponds to? So, did you guess it? It's going to be 100,000 electron volts. So that's a really cool thing about electron volts. If you know the potential difference, you know exactly how much energy that your charge is gaining or losing. If you didn't know this, you could always use this equation here. You can stick the charge of the electron, which is negative 1.6 times 10 to the negative 19 joules. And you could put a potential difference, which is 100,000 volts. And you will get the answer in joules. Now, we actually do need the answer in joules. So we can just convert from EVs to joules since we already have our answer in EVs. And remember, we saw in our previous, in the video, that we have the conversion factor. I'll put it here. 1 EV is 1.6 times 10 to the negative 19 joules. So if we already know 100,000 EVs, then all we have to do to convert it to joules is say we want 1.6 times 10 to the negative 19 joules on top and 1 EV on the bottom. That's using our conversion factor. And we can see it amounts to the same thing, that we are still multiplying 100,000 EV by 1.6 times 10 to the negative 19 joules. But I could very well ask you a question, how much energy does it gain if it accelerates through 100,000 volts, and all the answer choices could be in electron volts. So in that case, it's a lot easier to understand the relationship between the potential difference and the energy gained in electron volts. Okay, so that being said, when you multiply these two together, then you're going to get 1.6 times 10 to the negative 14 joules. That's the change in kinetic energy. Now we have to relate it to speed. Change in kinetic energy means final kinetic energy minus initial kinetic energy. And kinetic energy, if you remember from physics 1, is 1/2 mv final squared for the final, 1/2 mv initial for the initial. So this brings about another given. It's accelerated from rest, so the v initial is 0. So we can cross out this whole entire term. The only other given that we need is the mass of the electron, and that is, mass of the electron is 9.11 times 10 to the negative 31 kilograms. So we need to go ahead and solve for v final, multiply each side by 2 and divide by m, and that will get rid of the 1/2 m, so you get vf squared, and then just take the square root of both sides so that you can get vf by itself. So vf equals the square root of 2 over m, let's go ahead and plug that mass in, 9.11 times 10 to the negative 31, and then multiply it by the change in kinetic energy, which we had right here, 1.6 times 10 to the negative 14 joules. Everything is in the standard units, then we will get meters per second, and we end up with 1.88 times 10 to the 8 meters per second. So that is a huge speed, and that is what these particle accelerators do. They get these particles to really great speeds to make exciting discoveries. As long as your answer is less than the speed of light, then it's probably correct. If you don't know, or just FYI, the speed of light, we'll talk about it later, but it's designated with the letter c, and it's 3 times 10 to the 8 meters per second. So that's the speed of light. As long as you're less than that, then you're good. That's it for this example, everyone. I hope you like the electron volt and just see it as a different unit for energy. Alright, energy, energy, energy. Don't forget that. And I will see you in the next video.